Alright, hello. I got a video set up going here. I'm going to be using this to talk about DiffEq or DiffEqOperators.jl. And the reason why I'm doing it like this is because it's a pretty mathematical topic. There's quite a few people interested in doing this for things like GSoC, and I want to introduce where we're going with this library. This is very informal, so this is like completely unpracticed and everything. This is just for people who are interested in contributing. So don't think about this as like an information video, but I mean, you can use this as an informational video if you want. But yeah, so what this library is basically building towards is something called the Fokker Planck equation. That might be misspelled equation, or this is also known in math as the forward Kolmogorov equation. And so where this equation comes from, you can find this in a blog post that I have. Let me just pull it up here. So yeah, this is completely super informal. Don't take this as a... So if you go to stochastiklifestyle.com, you'll find this is where I have all my blog posts. Under stochastics, I have one of my earliest posts here is just what exactly is Brownian motion and why does it matter? And you'll find some more details on this topic of where this thing comes from. But the general idea here is that you can model a lot of random processes in two different ways. So if you have a random process where you have particles, right, there are two different ways to think about this, and one is the level of a single particle. If you take this particle and you say that it moves, right, so its position is some deterministic function, dt. This is an ODE. And what you can do is you can add to it. You can say that you have this other term on here, where this now becomes what's known as a stochastic differential equation. Right? And so stochastic differential equation is an ODE with randomness. That's stochastic just means random. And what this dw term is this is Brownian motion, and so here's why it's Brownian motion though. And it's because if you can think about this as single particles, or you can think about this as a group of particles. If you think about it as a group of particles, then you don't think about position. Instead, you think about what is the density of particles at a given location, right? So when you have a whole bunch of water particles over here, and maybe only a little bit over here, then you can think about it as you have a peak, where this is now your density at a given location. And what you want to understand is how this density changes with time, right? So maybe in time it smooths out, right? So more of the well, that'd be a little bit low. So more of the particles move everywhere else, right? It diffuses. That's what the particles do. And so in this form, so whenever you have one of these SDEs, you also have a dual equation which talks about how the probability density, so this is the probability density. Well, that's actually an interesting feature of this equation, and it's that if you think that all of the particles are the same, then you can either think about it as the probability that one particle is here versus over here, or you can think about it as the percentage of particles that are here versus the percentage of particles that are over here. If you have this ergodicity assumption of the stochastic differential equation, which is required for this, This is actually a way to define ergodicity, which is just that you have this mixing going on. Then it's the same thing to talk about probabilities as it is to talk about densities, as it is to talk about the solution of the SDE versus the solution of how this function evolves over time, right? This function goes to another function which is smoothed out, and that the evolution of that function is given by a PDE. So that is what we call the Fokker-Planck equation. Let me just make sure I have my notation the way that will line up. So yeah, the Fokker-Planck PDE is the change in this density over time, where this is this density is a function of time and space, right? Here the spatial location, remember, is the thing from our SDE. This evolves as f of t u u sub that has a is this not erasing right? Okay, so that evolves as that term plus g of t u squared over 2 d sub x x, why am I using u? Oh, let me use u then for the probability. So this function right here is u of x, and this goes to u of x at a later time. So this is u sub xx. Yeah. So, okay. And you can also write this as u sub t. So this is u sub t. It has some function here, u sub x, plus some function here, u sub xx. Now, remember, this function right here is what we call the drift term. This is the ODE that's associated with the particle, right? So this is like what happens on average or deterministically. Whereas this term right here is called the diffusion term. And it's the one that is how much randomness are we putting on the ODE, right? When we turn it from an ODE to an SDE, we put some randomness on it. The F function is the ODE, the G function is the amount of randomness. And when we come down to the Fokker-Planck equation, so let me just double check that I wrote it right. I think that's one simplified form. There might be other forms that you find. But this form is pretty informative, at least for what we want to be doing. So let me see here. So yeah, actually the derivative terms are around the... So I'm actually making the assumption here then that that's the issue. Okay. So oops, forgot that I broke my eraser here. So normally you see it like this. So remember, U is the probability distribution or the density, the amount of particles at a given location. X is that location, and T is the current time, right? So this right here would be u of tx, which goes to u at a different t, same x, right? Now, the first term is the derivative in space. The second term is the second derivative in space. And then this is usually what we call the Fokker-Planck equation. Another very important term is where if you have f of t x is actually just a function f of t, and g of t x is just a function g of t, then this actually simplifies to u sub t equals f of t u sub x plus g squared t over 2 u sub x, right? And so when you have a nonlinearity and another stuff involved, right? So this f function and g function in general can actually be functions of u, just not when you derive it in this way. It is more difficult, but the same numerical ideas will apply. So the reason why this is important is that this equation is the mixture of two very famous sub-equations. So if you go look up this, so the diffusion advection equation, also known as convection diffusion. So this equation has a bunch of different names given who you're talking to, but that's another way of writing it. Right, so you'll see that this is the second derivative part where they've actually taken the d. They define the d to be outside of there. That d is the same thing as our g, and this v is then the same thing as our f. But it's the same general idea there. So this diffusion advection equation is, it actually has two terms. So you have this convection equation, not oven, convection equation. There we go. Maybe in Wikipedia it's written as the advection equation. Yeah, so they have it here as the advection equation, but same thing. So yeah, the one thing that gets a little confusing about this, well, I think that they write it down best in the upwinding. So it's getting a little ahead of ourselves, but upwinding scheme. So yeah, when you have the one-dimensional linear advection equation, that's what they're calling it. Same thing as the convection, I think. I'm not a fluid dynamics guy, so I might be getting that mixed up. But anyways, so the one-dimensional advection equation is u sub t equals a u sub x. And what you'll see here is that that's actually this thing right here. So this is the advection equation. And over. So the reason why it's so convection, advection. I don't know why it's two words, but yeah, so the other term though, you'll notice is from the diffusion equation. So if we pull that up here, let me make sure that, yeah, I'm still recording. So the diffusion equation, if you pull this up, they don't actually have it written the way that we have it written. Okay. Why do they have to make things so complicated? But really this U sub T equals U sub XX, that is the heat equation, which is the diffusion equation. Right, and you'll see that this over here, that is the heat equation, the diffusion equation. So that's why this is called the advection-diffusion. Equation. The convection diffusion equation. Now its relation to this being actually from a stochastic differential equation is called the forward Kolmogorov equation. Right, so that's saying that probabilities of an SDE evolve like this, same equation. And then you also will see in physics literature that this is the Fokker-Planck equation. So the reason why it's called that is that's because it describes how a fluid spreads out, where if you have a fluid which has properties of drift and it has the ability to diffuse, then the densities of the fluid evolve like the Fokker-Planck equation. So this is from the field CFD, computational fluid dynamics. This is how people in math tend to talk about it. This is how people in other areas of physics talk about it. And then sometimes people in like biology or finance / economics tend to, for some reason, call it the Fokker-Planck equation too. But these are all words to describe the same basic thing, which is this guy, or its nonlinear forms, where you can now start letting f depend on u, or you can put them inside of the derivatives. It doesn't really matter, right? So this is the more general form. You can actually put u's in there. That's cool too. So DiffEqOperators.jl is going to be taking this as the key equation that we want to build towards first. Because, I mean, you have people who in computational fluid dynamics who are using this to study how fluids evolved, right? This is like this is also used in things like climate modeling to see how heat flows with so you have the diffusion part with the G, you have how wind is going with the F. Another place where this is used a lot is in biology, where this is how chemicals flow inside of a spatial biological organism. And then a lot of people use this for the Fokker-Planck, or the Forward-Kolmogorov version, which is you have a stochastic differential equation. You want to get the probability distributions as they evolve over time. And that is then something that's highly used in, say, economics or finance. So for all of these reasons, so many disciplines want to have the solution to this. And so this is a good equation to start building towards. And now the other thing, though, is that these the heat equation and the advection equation are two canonical PDEs to try to deal with. So the advection equation, u sub x. Now, I didn't introduce it, so let me just say that this is the same thing as writing du of tx equals a du dx of tx. And once I start writing that, you can see why I stop writing partial derivatives and just start using subscripts for the derivatives. So this is advection, and this is diffusion. du, I'm not even going to try to write that one. So u sub t equals u sub xx. We always put a constant a here for the advection equation because it's really important for the advection equation. And we'll get to that in a sec. So you can see where all these names are starting to come from, and what these do. So basically, this diffusion term in the stochastic differential equation describes how the molecules, how this guy diffuses away randomly. And if you have no drift term, then the Fokker-Planck equation says that the probability distribution evolves as the heat equation. So that's basically just saying that if you just have heat without wind, then you just have diffusion. Oh, that makes sense, right? This other equation, though, this drift term, gives you the advection equation. And if the solution to the advection equation looks like if you have a bump here, it evolves over time to just move. So the advection equation is how bumps move. And then the diffusion equation is just if you have the thing here, then you have the thing spread out. The diffusion equation is how bumps spread. And so what's interesting is that even for the nonlinear case, like if you assume that you have enough linearity locally, right? That's the common assumption whenever you want to talk about anything differentiable. Then the numerical methods for handling this tend to be that you can handle the two of these separately. As long as you can understand how to handle the advection equation and handle the diffusion equation, then you are good. So, where do these methods come from? I'm going to start with the diffusion equation because it's simpler. So u sub t equals u sub xx. This standard way that you solve this is you first start by saying, well, I have this function u of t x, and what I want to do is I want to cut this up. Right, so now instead I have, at a given time point n, I have u sub I. Right, and then you have u sub n I plus 1, dot, dot, dot. And so now if you think about it as a 2D grid, right, so we have I and n, then these are all your spatial points. And then what you do is you use your previous solution to step forward to your next solution. Where, and so the question is, how do you use, if this is going up in time, and then this is x, right? Now it's all discretized. How do I know, given the concentration of the fluid here, how do I know what the concentration of the fluid will be at the next time point? And so what you can do is via a Taylor series argument, you can show that du or dt is at each of the I is equal to u sub I minus 1 minus 2 u sub I plus u sub I plus 1. That's the, sorry, so used to stochastic differential equations. So u sub I prime equals that. And so normally, now let me relate this back to how you've probably seen this. So normally what you would have done is you would have said, okay, let's do a discretization here and discretization here. So you might have seen this written as u sub n plus 1 minus u sub n I over delta t equals, oh, I forgot a delta x squared here, equals u sub I minus 1 to the n minus 2 u sub I n plus u sub I minus 1 n over delta x squared. You probably have seen this written like this, and this is called the Euler discretization of the heat equation. And the reason why this is done in class is because this then gives you a very simple way to say, okay, if you move this guy over, then you know how to. This tells you exactly how to from these three guys calculate this guy, and so this is called the, well, this is the Laplacian. This is a 3-point stencil for how to use three points to compute one forward. But instead of writing it like that is a nice way for teaching, and that is a way that a lot of people use this, but that's actually not the right way to program this, right? If we just keep this time derivative as the derivative, then you notice that u prime of I equals this over here. This is now actually a system of ODEs. So we can just stick that ODE into a numerical integrator, and so this is written in a form for what's called method of lines. Right? Because now, if you have an array, if you have this array, which is just your u sub I plus 1, right? Then you can write this as your derivative function on this ODE, put that into any numerical ODE solver, and then sundials will give you this fifth order adaptive, fifth order adaptive time stepping, and you don't actually have to come up with your own time stepping scheme that's adaptive or anything like that. So this method of lines way is a very practical way to be able to make use of other tools, which is important when we're doing software development. Right? So when you're not doing software development, that's why they leave this out of class. But okay, what this shows us though is that discretization of space can be done separately from discretization of time. And the discretization of time, that is then done by an ODE solver just by writing this out as an ODE on an array, where the array is our points of the values of the concentrations at each point in space. So another way that this can be written, though, is instead of writing this, plus 1, 1, minus 1, with the 1, minus 2, you say that this is the stencil 1, minus 2, 1. Right, and if we actually write out a matrix, which is minus 2, 1, minus 2, 1, 1, 1, minus 2, 1, and now we have zeros, right? So this is a tridiagonal matrix. If we call this A, then our system of ODEs is actually just u prime equals A times u. And so this right here is just a matrix, or more generally a linear operator, that when we apply it is the spatial discretization of the PDE in the finite difference sense. So this discretization, where we say we take a delta x and we use that delta x, that is called the finite difference method. So this is the finite difference linear operator for the Laplacian. But that's not all the details that we have here, because this u prime equals this is not actually true. We've actually chopped off that there's an O of delta x term, or delta x cubed, because it only gets the first two derivatives right. So the way of saying that is the second order finite difference operator for the Laplacian. So instead of using 3 points, you can use 5 points, and then you can get one that is a higher order accuracy. Let's interpret what all this means a little bit. If you think about this as the particles in the fluid, what you're saying is that all of the particles in the fluid here move either to the left or to the right. Ones from the left come in, ones from the left come in, ones from the right come in, and that's how the diffusion works, right? You're moving to the side, they're moving to the side, and naturally you'll get a solution that has everything spread out. And so what DiffEqOperators is all about is getting a operator. So if you have an operator, so you want to do like the derivative operator of 2, 2. What this means is the second order of the second derivative. Right, so that would mean that you want to take u sub xx, and you want me to spit out this a, where ax is the same thing as u sub xx, but it is some approximation. That's what DiffEqOperators is all about, right? So this is the one everyone knows. It's only second order. How can we do any order? Well, this is something called the Thornburg algorithm. Now, the Thornburg algorithm, what it does is it tells you, like, if you want the second derivative at second order, then it spits out that, this 2 of 2 is this stencil. 1 minus 2, 1, where then you just apply this as though it's a banded matrix to U, right? So this 1 minus 2, 1 then says that's how you then go through each part of the array, and you say from right here, let's minus 2, let's take this guy in the middle here, we minus 2 him, we plus 1 here, we plus 1 here, then we go the next one down, we apply that stencil, right? So that's the second order one, but DiffEqOperators.jl through the Thornburg algorithm gives you any derivative with any order. The other thing to note is this is called the centered derivative because it is the derivative centered around the point that we're taking the derivative of, right? So the derivative if we're taking the derivative of this point, we're using one value to the right and one value to the left, right? We're using I plus 1, I minus 1. This is different than what we'll have to do for the advection equation. So let me try to just pull up some of the code here now. So I'm just checking for the library on Google. If I go down to the test here, you'll see that the interface just looks like this. And you'll see this is exactly what I was saying, what the derivative order is and what the approximation order is. And so now this is already set up to use the Thornburg equation to get those out. Let me walk through that a little bit. I wonder if I even have this installed. This equation is old and slow, so I'm not sure I would be able to actually run stuff on it. But we'll see. Actually, I can use Julia Box. That'll work. Oh, but Julia Box won't have it. Okay. Because this library is not released. Interesting. So let's take a look at what this thing actually does. So this derivative operator, right, all it needs to know is what is the stencil coefficients. So what it does is it presents itself like a matrix, even though it's not really a matrix. Because in Julia, right, in Julia, you can say, you can define A mol B. So A mol B in Julia is the same thing as star, except it's in place. And if you want a good introduction to in-place operations, take a look at my the differential intro to differential equations in Julia, and I go through what this is. So A mol B of output A B is the same thing as writing the output equals A times B, except here you are writing into an array that's already been created, and here you're creating the output array. So you can define star by defining A mol B and just saying, build the output array, make the output array match one of the inputs. You actually have to make sure that the size is right, but make the output array match one of the inputs and then call A mol B. So that's all that star means. And so the core of what how matrix multiplication is defined is always in the A mol B, except for static arrays. Let's ignore that. So okay, so if you know the stencil coefficients, though, right? So if you know that you have or if you know that you have 1, -2, 1 as your stencil, then you know that you want to apply it down the array, like, you go take this guy, you go -2, 1, 1 to give you the next guy right here. Right, you know that that's the same thing as this tridiagonal matrix. So what DiffEqOperators does is it overloads A mul B to apply the stencil as though it was the matrix, even though the matrix is never constructed. And so that's why this right here holds all the information about what that would be. So it has what the dx is, and it has the stencil lengths. Everyone wants to contact me right now. So yeah, it has the stencil lengths and the stencil coefficients, and from that information you can define these stars. Just use A mul B, and then further down we should have the A mul B definition. I'll get to the boundary conditions in a second. Yeah, so there's some indexing functions, so that way it looks like a matrix, but remember the matrix isn't actually there. It's just multiplying by unit vectors, because that's another way to define indexing. So yeah, so A mul B is defined by these convolutions. So convolved left, interior, left boundary condition, right boundary condition, interior. Let's look at the interior because that's what I talked about. Oh, and it scales afterwards, and that's just by the dx squared. That's if it's a second derivative, or then it's dx squared, and etc. So how do these convolutions work? So the Thornburg algorithm, that we already know is quite correct. That just calculates what the stencil should be, and that's what's in Thornburg.jl. I think we should probably refactor this to not be in boundary operators. But the interior convolution is right here. And basically what it says is you go to each spot, and then you go to each part of the array, and you apply, you go to this I, and then you go, okay, let's do this coefficient here times that value, this coefficient here times that value, this coefficient here times that value. And so this convolve interior is the same thing as applying that stencil to the whole interior. So the part that I've left out is the boundary conditions. So one thing that you might want to say is maybe when you get to here, you look back one, you use that value, and if you have the boundary condition that u at the boundary, so u of t, let's call that just the boundary b, if you say that that's 0, right, then when you look over it, you say that's 0, then it's the same thing as doing 1, -2, and lopping this off. So if you're to do that, then your matrix would be the same thing as though, well, that's what I wrote here, right? So you lop off the 1, -2, you go down, go down, go down. This is 1, -2, and the 1, it falls off. And so for the Dirichlet boundary condition, you just need to make sure that whenever you hit the edge, you don't use any values, right? You just make it 0, except if you actually have a value a. So if u at the boundary is equal to some value, that's a very bad name for that. Let's rename that to k. Then we need to make sure that instead of using, since we don't have anything here, now we need to do a 1 times k, right? And the way that we define this too is that if we have a bigger stencil, right, so if we only have 3 points, you're only going to go 1 point over. But if you have a bigger stencil, like let's say you're taking 5 points, then we can extrapolate and say that the boundary condition all the way over here is still going to be k. And we just need to make sure we apply the stencil all the way over there. So that's called the constant extrapolation of the boundary. So okay, that's how you'd handle a Dirichlet condition. Now Neumann boundary conditions can be a little bit harder to derive. But at least for the case of Neumann is 0, what you can do is that you can say that this 1 would have gone over here. So Neumann condition of 0 means that the derivative should be 0 at the boundary. And if the derivative is 0 at the boundary, then that's the same thing as saying you've reflected over the boundary. So if you take this 1 and you reflect it over, then this becomes a 2. And so you get a 2 minus 2 here. The reason is because now you have these coefficients match, which means that the derivative at this term is going to be 0. But you might have started to notice that there's something a little messed up here, because I said the derivative at this term is 0. So in the Neumann case, I've written this matrix such that the endpoint right here, this is the boundary. I've written this here saying that this is the boundary, this last guy here is the boundary. Whereas for Dirichlet, what I've been saying is that all of these guys in the array are interior, and the first guy off is the boundary, the first guy off is the boundary. Let me describe one more case too, and it's the periodic case, where we assume that this array, if you index it downwards, the one after this guy is the same as this guy over here. That's called periodic, and so you can minus 2, 1. Where does this guy come from? Well, the value that you'd grab would be the value that's the value that you'd grab over here would be the same as the guy that's over here. And so that's how you can get, that's how come when things fall off, they instead go to the other corners. That means periodic, because if you actually take this and apply it, you'll see that that's the same thing as saying minus 2, 1, go around, 1. Right, so check it out yourself. Make sure that that makes sense to you. So you have periodic, you have Neumann, and you have Dirichlet. The difference is this one says that the boundary value is a certain, you give it a value. The boundary is equal to k. This one you give that the boundary derivative, so the d t of u at the boundary is equal to some value. And then this one you just say, you redefine your space to say that, well, you flop around, right? Either way, you have a nice boundary condition. And then you have that the Robin boundary condition is some mixture of Dirichlet and Neumann. Let's not go over that for now. But okay, there's a conventional mix-up here. The issue is that for Dirichlet, I said that the boundary points are the first one off. The Neumann points are the ones on the ends. And for periodic, can you guess what where the boundaries are? Well, like if you say that, what you were really saying is that if you have n as the endpoint, I already used n, let's call this m as the, over here, if you have this as u of m, then u of m plus 1 is the guy over here, is equal to u sub 1. So in this case, you actually only have you basically only have 1 point on the boundary, but what I'm saying is that I'm putting the boundary on one side or the other side by your convention. And so this has no boundary points in the array. This one has 2 boundary points in the array. This one has 1 boundary point on either side, depending on how you've defined it. Even more confusing is that you don't actually have to put this at the points, right? So I said that, this is like, if you go delta x over, then you have u of t, let's just say we start at 0, this is delta x. next one over is u of t 2 delta x, right? This is what we're then calling our approximation of u sub n 1 and u sub n 2. Instead of placing these at the actual delta x's, you can put them at the half points. So if we have our space, you can say that our first is going to actually be u sub t delta x over 2, u sub t delta x over 2 plus delta x, and then you're going to add delta, you're going to make them all the same space apart, and delta x, right? So this is the normal one. This is called the centered discretization. Now, if you do the centered discretization, then notice that you have 2 points which are not on the boundary. Your next points are off the boundary. What you can see is that this actually makes sense with the way we've written down periodic. It doesn't make sense with the way we've written down Neumann, and it makes sense with Dirichlet. This one, it makes sense with Dirichlet if you have n many points. It makes sense with Neumann if you have n plus 2 many points. And it doesn't actually make sense with periodic because, well, you can make sense of it with periodic as long as you say, as long as you make one of the points your boundary. But this is then very confusing to the user, right? If you're to ask the question of, how do I supply my initial condition? I mean, where exactly, how big is this array supposed to be such that it matches the operator that you get out? And so that's actually the biggest issue right now that we have in DiffEqOperators.jl, and it's the first one that we should probably tackle. So what I describe here is all the different ways that the operator should look like, given the different definitions of how, if you have the boundaries on the array and you have Dirichlet 0, our boundaries are off the array and Dirichlet 0, this is what I showed before, and it's just the application of the stencil. So Dirichlet 0, I mean Dirichlet where you say that k equals 0. But now if you have the boundaries in the actual array, right? If you have the so let's look at the case where you have that the boundaries are actually in the array and you have a Dirichlet condition. So you say that this is k, right? The user actually puts that the end of the arrays are k, and then you want to apply the derivative on here. What you'd notice is that the stencil that you'd actually have to use would look like this, where you'd carry it all the way to the end. The reason why is because this 1 would then just grab the k on the end, and so we'll use the right value. So this is a nice way to be able to write the Dirichlet such that the boundaries are on the array. And if you use that style, then it also matches with Neumann, so that way the boundaries are on the array. Right? So that way the boundaries are on the array. And so then what I write down here is that there's also a way of writing the periodic such that the boundaries are on the array. So we can come up with a way of writing. Notice then that it's not at the very ends here, because what's going on is that if you have the boundary on the array and it's periodic, then this point is actually equal to this point, and so when you wrap around, you have to wrap around more than 1 over. And that's what this boundaries on the array, when you wrap around, you have to, right, when you wrap around, you skip this point because this point equals this point, and then you grab this point. So what's nice is that you can write these linear operators in a way such they're consistent, and they will all be able to be used with the same convention, where we say that we use the non-centered discretization and we put the values of the boundary points as the last points in our array. The problem is that's not how DiffEqOperators is currently implemented. Instead, it mixes the different conventions given different boundary conditions. So right now we have, it's as I described before, you have the boundaries off the array if it's Dirichlet, you have the boundaries on the array for Neumann, and you have one, and you're actually using the centered discretization if you're using periodic. So yikes, that's crazy. But the way to fix this is to, so in these equations, if you have these convolve left and convolve right, they're basically the same thing. We might want to find a way to use dispatch to fix this, but for now, what we do is we have, these are how the boundary conditions are applied. And so we say that the number of boundary points, so we have, whenever we have a point that's fallen off, that's one of the boundary points. And so we know how many fall off by the size of the stencil. So if you have 3 points in our stencil, then you only will have one row where you have a point falling off. If you have a 5-point stencil, then you'll notice that you'll have 3 rows where you have things falling off, because you always have to get where the center is on the edge. 2, yeah. It will be 2. I was off by 1. So this boundary point count is just the number of that's just the number of rows where we're going to have to loop over that have to have a special boundary condition, because if you're just to apply the stencil like we did before, then you'll index off the array and it'll just give you an error. So we have to make sure we take over the indexing when we're at the edges here. And so this says, oh, for this dispatch is for Dirichlet 0. This is how we're going to handle the Dirichlet 0 boundary condition. Dirichlet 0, remember, just means that it's Dirichlet condition where k equals 0. And so we have separate dispatches then for these different types of boundary conditions, where the boundary condition is just held as a symbol for in a type parameter for the derivative operator. And so let me just, so let's look at how those are implemented then. So those are right and left. So the reason why it's written like that is so that with the function call in there, so that way we can have the same code here for the right and left. And so what Dirichlet 0 does is it just finds out what is the highest and what's the lowest it can actually index to, and then it adds together all the points that are inside of that, right? It chops off the array when it falls off. This other one needs to make sure that when it goes over, it adds the right values to it. Make sure that you add whatever this k was, because this definition didn't have the derivative on the end. So instead, how this definition needs to change, if we want it to be compatible with saying that the boundary condition is on the end, what it really needs to do is find out when you're indexing off the array, and when you are indexing off the array, just make that index be the same as the last one. I think that might be what's going on here, but we might need to do a test for that. For periodic, we need to make sure that when we take into account that the boundary is the value at the end, and it's the same on both ends. So we should do an error check for that, and then when we go over, we need to make sure that this rem1, it's actually going to, so this rem1, what it is calculating the remainder of how far off the array you are, so that way it can loop back over to the other side. But really what it needs to do is it needs to loop back over and add 1, so that way it skips over the boundary. So I mean, you can go back through this, and if you look at the stencils of what they should be, and you can sit down and derive them out yourself, or you can just ask me at any time how you can actually derive these. But we need to make sure that the loops actually correspond to these ones that are boundaries on the array. And then I describe a few special cases that we should also handle. But But yeah, that's the basic idea there. We need to make sure that the looping actually works such that we match all this one definition. And when we do that, then we need to go back to things like the heat equation and use an analytical solution and make sure that when we use the Dirichlet version of this operator, so ODE problem. So the nice thing about these operators is that this A is also a function of UPT, which is the same thing as doing A times U. You can find that definition inside of the DiffEqOperators library, but what this means is that if you just pass the A, then you are to an ODE problem, then it'll solve the method of lines ODE defined by that operator. So this is a quick way of saying, here, let's get the operator for Dirichlet, where these are boundary conditions on the end. This creates the ODE problem for that, and then we solve that, and then we can check it against our analytical solution. But this ends up actually being broken right now, and the reason why is because this convention mix-up, where this way of writing the initial condition didn't actually take into account how we define the space properly. So it's mixed up with the actual analytical solution. Oh, actually, this one could also be numerical error. So we do need to go back through this and make sure we got that one right. So next question is, why do we have the boundary conditions like this? Well, for Dirichlet, we had that because the boundaries weren't actually on the array, right? So if you have, if you're applying the stencil in Dirichlet, where do you actually get this value for what the boundary is supposed to be if you don't put it on the end here? Well, we had to store it inside of the operator, right? So that was the function that or constant that we stored. If we put it on the end of if we make the end value be the actual derivative, then we don't have to do that anymore, right? Because then you just say it's that endpoint that the user gave you. So that's quite nice. That fixes that issue. For Neumann, we still have to have store the function for what the derivative is at each time point, because that derivative isn't something that's given in the U array, and so that's what's being stored here. This is what the values for the derivative are, and it should be holding it internally such that these can be a value or function. Let me describe that a little bit. So the DiffEqOperators interface has two things that it can do. So an operator can do the stencil, right, where this applies the stencil, but also has a separate function, which is update coefficients of the operator at UPT. And what this should do is it should make the operator current to this time point. So if you have like a Neumann boundary condition that is dependent on time, then this should update the coefficients in the stencil such that A knows what time it is, so that way the next application of A times U will use the right boundary condition. So why is it done like this? Well, because if we have update if I write a code that's just like update coefficients and then do A times U, this code then works for any A that satisfies the interface. So any A such that you have this dispatch of update coefficients and a dispatch for what the matrix operation means, then it'll work inside your code if you have it set up like this. So this makes it so that the other codes that are using your operator don't have to know anything about the internals of how it's implemented. It just needs to know that it can be updated to specific time points, and then here's how you apply it. And so anybody can write these codes that utilize these operators without having to know how the internals of the boundary conditions or any of that works, which is then nice because we can come up with all sorts of different operators too without having to worry about them matching at a deeper level. There's a little bit more to the that can be used from the DiffEq operators interface, but let's stick with this for now. Because they're non-essential for what we're looking at. But okay, I think that captures all of it. So we have these tests which say this is how the heat equation should be performing. On some boundary conditions, it lines up with what we believe. In other cases, it's not working, and that is because of this convention problem. And so we need to go back through and fix the boundary conditions. And so the first basic test is the derivative operators test. That's this one that makes sure the indexing and things work. This is all good. But as you go down to some of the boundary condition tests, you'll notice that there are some things failing. So the way that the boundary condition is working works with the way that we thought it should. It's just that doesn't match the right convention, and so when you try to solve a real problem, it doesn't line up with how you normally define this initial condition, and that's where things fail, right? And so the goal here would be to fix those boundary conditions, change the way it's defined in this Dirichlet to match up with this new convention, and then make sure it solves the heat equation correctly. So that's the heat equation discretization. And the key idea for the heat equation is that it uses a centered discretization, right? You have the point in the center, and then you have the points on the side. And the reason why that makes sense is because you're describing how things diffuse, how things spread apart. Mathematically, you can show that this is stable for a stable way of solving PDEs, or this type of PDE, even at higher orders. So I've written everything as, 1 minus 2, 1. The question is, why do you want a library for this? Well, if I was to ask you, write down the 6th order discretization of the PDE, that can be more stable and give you less numerical error per step. But now actually writing that algorithm out, I'm not even sure what the... let me actually look up on another computer right now. 4th order discretization of the Laplacian. I'm not even going to try the 6th. Well, here, I have another computer here that I can actually pull up DiffEq operators on. This is kind of a tangent, but I think it's important to... Yeah, I'm getting you this video. Don't worry, bro. So I'm pulling it up. Basically, the thing is, nobody really knows the higher order coefficients by heart. And if you had to write it down, you'd probably have to go derive it from Taylor series and it's not fun. But DiffEq operators, you just say, give me this order of the discretization for, second derivative, and then you have it there. That's quite nice. So on this other computer, I'm pulling this up. Just one sec here. Okay, I'm getting everything installed and compiled right now. Oh, yeah, that's fine. What did I say that the stencil was? A.co. Yes. So if you were to look into the library and then ask, okay, so remember that it was stored as a.stencilcoos, and I just found that out by looking at the definition of the operator. So the fourth order stencil is okay. That's actually how can I send a message to myself for this? Well, it's crazy. Yeah, I'll send the message to myself on Getter. No one will know what this is for. So if you're to ask yourself, I want the fourth order derivative, and I want the stencil for the fourth order derivative, and I want it to be at fourth order itself, then that is the stencil that you compute if you want it in big floats. And then if it's not in big floats, it's just smaller. So it's something with like a 1.3, minus 1, 4. This is not something you'd want to be computing on yourself, but with DiffEq operators, you just say, I want this order, this derivative, and it gives you back that stencil, and also an operator such that when you use star, it will calculate that. So when you're taught in class 1 minus 2, 1, that is less stable, and that is also a higher error. This gives you an easy way to get to the better algorithms. So that's for the centered discretization. But the next thing that let me make sure this is still running. Okay, cool. My surface seems like it's about to die here because of that fan. So the diffusion equation uses centered discretizations. And the reason is because what you're modeling is how things spread out. And I'm saying the reason is in some very high level way. In reality, the true reason is because if you do this, this is a higher order and it's stable. Now the advection equation, what you're modeling is how this bump, it moves forward. And so even though technically the centered discretizations work, you don't actually want to be using the centered discretization here because it's known as unstable. The reason why it's unstable is because if this delta t for how time is changing is too large, then this discretization will actually mess up and it'll go to infinity. You can read all sorts of things on that. So what you do instead is you use the non-centered derivatives. So the derivative here, so you use I minus 2 plus 1 minus 1. This is the centered derivative because you put this guy in the center. Now let's look at the derivatives when you have things on the side. The easiest approximation, so the first order approximation, the derivative, right, is just the forward minus the backwards divided by delta x. So this is second order. So the first order discretization that is centered would be you go u of I plus 1/2 minus u of I minus 1/2 over delta x. This would be the first order centered, right? Where you're actually still centered around the point. But now the first order forward derivative is just u of I plus 1 minus u of I divided by delta x. Right. And now what's interesting about this is that this is just using the information in front of you. So if you're right here, then what you do is you take the information in front of you and you use that to compute the derivative. Now, that might make sense if what you're trying to do is move forward, right? It's basically saying that you want your information to be in front of you. So what you actually find when you do the stability analysis of this is that the only discretization that you should be using for the advection equation are these forward and backwards derivatives, where the backwards derivative is u of I minus u of I minus 1 over delta x. Now the question is, which one do you use, the forward or the backwards? that depends on whether you're moving forwards or whether you're moving backwards. And if you're to look at the equation u sub t equals a u sub x, whether you're moving forwards or whether you're moving backwards is this coefficient here in front of the x. So that's when you look at this upwinding scheme. The basic upwinding scheme is when you're moving forwards, you use the backwards derivative. When you're moving backwards, you use the forward derivative. Why am I saying that? Well, if you're moving forwards, then what you want to make this value be is you want it to be the value that's back here. So when you're moving forwards, when a is positive, you want to use the backwards derivative. I think I said it wrong before. Now this is correct. When a is positive, you're moving forward, so you want to use the backwards derivative, so that way you update this point to be what this was. When you're moving in the other direction, right, you want to make this point here be the value that you used to have over here. That's another way of saying you're walking backwards. But you walk backwards when you have a less than 0. And so what the Upwind discretization scheme is it's just when a is greater than 0, you use backwards differencing. And when you have a less than 0, then you have forward differencing. So now these are called the upwinding schemes. And this right now, remember, is just the first order forward or backwards discretization. You have the that's normally what you're taught in class as the upwinding scheme, but it's only the first one, and it's the one that has, of course, the most error. So the higher order ones are just using higher order forwards and backwards discretizations, right? This is the first order backwards difference. No, second order backwards difference equation. This is the second order forward difference equation. And so now the upwinding scheme there is just check which direction you're moving in and apply the higher order forwards and backwards discretization scheme. I said before that the Thornburg algorithm, right, gives out this stencil for how to do any order for the differencing. Not only does it do the centered differencing, but it also gives you out any of the forward or backwards difference stencils. So it actually only gives the forward stencil, but the backward stencil is just it flipped. So that gives us all the information we need to be able to calculate this. And so the Thornburg algorithm, once again, gives out a stencil. In this case, it would be the stencil, depending on our definition of forward and backwards, it'd be like -1, 1. That's the first order one. And now say the second order scheme, what it'd put out is 3, -4, 1, right? And what this means is that as we go down our array, we would take 3 this value, -4 this value, 1 of this value, and then we'd put that as our next value right here. But if we had the coefficient reversed, then remember, then we'd have to do, instead of these 3, then we would do these 3 to go here. So then this is with just a constant a, right? This is where we're talking about a as a constant. But now let's say a is something of space. So let's say we have u sub t equals a of t x u sub x. Then when we discretize this, we have a sub n of I u sub x. Well, u prime equals, now let's also do the spatial discretization for a method of lines. So you have ODEs for each point in space. These are given by this A, and now we have the upwinding operator, this big A, U. This upwinding operator needs to take into account this A, because this is the local direction of how the hump is moving, right? So we can have the given different a's, we can have it moving forward here and backwards over here. And so what we need to do is we need to have not only know what the stencil it is, but it also needs to know the direction. And that's exactly what these upwinding operators are. So if we open up the code in the library, we go into the source here, derivative operators, go to the Upwind operator. You can see that it's actually very similar to the other scheme, except it has the directions. So when it calls the Thornbury algorithm, which is in that form.jl, it gets the one-sided derivatives, and then it applies, and then it sets up this operator to use that. Now currently what it does is it takes in directions as nothing, right? So when you do update coefficients, it can update what the stencil is, so it updates the boundary conditions. Boundary conditions are thought about just the same way that we had before, except now we just have to take into account that you will probably only be hitting the boundary on one side. Yeah, so in here you can update coefficients with the directions. The issue with that, though, is that if you had this interface where you say, okay, let's update the coefficients in a times u, you will not have known to update the directions in this generic form because the upwinding scheme, these upwinding operators are acting differently. So what this actually should be doing is this operator should hold on to what this a function is, so that way when you call update coefficients, it will just know itself to update the directions. So that way when doing a times u, it will be doing everything with the right directions for that given time point. So that's one thing that needs to be done with the upwinding scheme. The other thing is that we just need to make sure that we have the boundary conditions for this all correct as well, just like we need to be working on the boundary conditions for the other. So if you go into the test here, you can see that there's 1D advection. This equation seems to be being solved. But then when we go to the KDV equation, let me pull that one up here. It's just this guy. This is another equation where you want to be using these upwinding operators, and you want to do it on the. Basically, whenever you have odd derivatives, you usually want to be using upwinding operators, and when you have even derivatives, you want to use centered differencing. That's not always the case, but if you go through and do stability analysis on different PDEs, that is pretty much usually the case. So if we can build a library that does this, people can solve all sorts of PDEs by just guessing if that's true. That's a little tidbit. So we actually know for this KDV equation what the solution should be, and so that's what this equation is doing right here. It builds the upwinding operators for the discretization, it solves it, and then it's not getting to the right solution. And part of the reason could be because of this convention difference, right? So when we define the operator, is the boundary on or off the array? Are we defining their initial condition such that that's true as well, or should it be centered? Those are things that we really need to check, and we need to make sure that all these things are correct. And then when they're all correct, that's when we should have it lining up to give the same solution as the true KDV equation analytical solution. So that's where the upwinding operators are at. Now I just want to finish up by saying how this all comes together. When you actually want to solve the Fokker-Planck equation, as I said before, the discretization schemes on the two parts usually come together to give you something that's stable if you're stable in the two parts. this is because of the local linearity of the problem and that all numerical schemes tend to exploit. It's not always true, but it's true in this case. So if we have a way to solve the advection equation, we would use the upwinding operator here, we would use the central differential operator over here, and we'd have something that would solve the KdV equation, or the Fokker-Planck equation, by outputting a u prime equals that is method of lines, and then we can put that into an NEODE solver. Now you can always, of course, you can write that out yourself, where you do the first order version here, the second order version here, but by using it with the DiffEq operators, you can then easily get what the fourth order version, and have a fourth order version of solving the Fokker-Planck equation in total, right? So it'd be an easy way to then scale it up and get the higher order discretizations. And so that's what this is all working towards. So that's why, I hope that explains why our test cases are this. That explains why we're looking at the heat equation, or that's a test equation with analytical solutions that we can make sure we have high order derivative operators for. Then we're also looking at the advection equation because that's a simple one which captures the problems of upwinding, which has to have direction, but also allows us to test with an analytical solution how our derivative operators are doing, make sure that we have that at the right order, and when we put them together, then we can have a higher order fast thing that solves the Fokker-Planck equation. A few other things I just want to mention when looking at this library is that notice that the matrix here doesn't actually exist, right? We're not actually storing the full matrix. We're only storing the stencil points, and then we're applying the stencil. So like for the heat equation one, this 2, 2, it's only 3 points that we're storing, and then we're just defining a function a mul b that will apply that when we do star. So when we do the matrix multiplication, it's actually just calling a function, and it's calling this function here. What's nice is that this is set up to use multi-threading, so it's already going to be happening in parallel. So another way that we want to extend this library is just to make this calculation right here work on the GPU, or work distributed parallelism. The reason why that would work well is because we don't actually have to put the matrix on the GPU or put anything, put the matrix parallel, because there is no matrix that exists. So if we just put the user's array on the GPU, then we can just apply this stencil on the GPU in parallel, and then just get the answer back from that. So other places that we're going are trying to exploit this is called a matrix-free implementation. We can exploit this matrix-free implementation in order to have a more efficient parallel implementation. And let's go back up here to, so yeah, you can see that the tests that are broken are like KdV, Robin boundary conditions. Most of these things are related to the boundary conditions. And we might want to also have more boundary conditions like ghost points. So there's a few other things to mention. Oh yeah, so the Hamilton-Jacobi-Bellman equation, which shows up in one of those issues, that's highly related to this. If we have these operators, we can then write down the discretization of that equation. So we don't need to look at it directly yet. We need to look at these simpler equations to make sure we have everything correct. And then it'll basically come for free that we'll get equations like Hamilton-Jacobi-Bellman equation. One other thing to look at is 2D derivatives, or also ND derivatives. So I've always been writing this as a U, and what this actually does, right, when we do a matrix multiplication, is this takes this row and applies it down there. This takes this row, applies it down there too, right? So matrix multiplication on the right acts by rows, but remember that matrix multiplication on the left acts by columns. So if we instead make our U equal to, if we make this be the y-axis and the x-axis, and so this is a 2D discretization of space, then what you'll notice is that a times u with a derivative operator is a y, that's a y derivative. Right, so if we use the heat equation 1 minus 2, 1 over here, then this will do diffusion along the columns, and that would be the same thing as u sub y, y. Now if we do u times a, that'll be applying the diffusion equation along the rows, and so that's the same thing as u sub x, x. And so what you can see is that because of the linearity of derivatives, you can write down these kinds of derivatives as just, au plus ua, or maybe these have a different constant in there or something for different derivative or different diffusions, or delta x versus delta y's. But in general, this just means that a 2D discretization can be written as either left multiplication or right multiplication by these operators. And so these DiffEq operators, even though they're only defined for 1D, extend to 2D. In a similar way, if you use something like, let me see if I could just pull it up here, TensorOperations.jl. The same idea extends to higher dimensions as long as you define your a way of multiplying by the tensor. So if we want to do 3D, we need to come up with these tensor operations such that we can apply the operator along different slices. So if we had a 3D discretization of space, then we make u of I, j, k equal to, this cube of points. Right? So if we have this cube of points, then that means we want to apply x derivative operations going across the x axis, all these different ways of slicing this cube. And so we need to come up with a way of writing these tensor operations. But even in that case of 3D, it still comes down to doing the 1D stencil along different axes. And so another thing that we want to solve is how do you make 3D star look nice? Right? What's the right API for that? But if you can do 3D, then that means you probably have already gotten to ND, so ND, end derivative, or n dimensions. So that's what some of the other things in the issues are talking about. Just how do you work up to higher dimensions, because the matrix equations only have left and right, so they can only handle 2D, but tensor operations can handle these higher things, but we don't have an API for making that easy. Let me just make sure I've covered it all. So one of the other things that we need to make sure we get done here is that we have that everything is defined well for a times u in many of these cases, but even though we have the stencil correct, if the user actually wants to use this, like say in PET-C or something like that, they need to get out what this operator is. They want to get this as a matrix. So what we want to give them is we want to give them this as a banded matrix. Right, because all of these stencils are going to be banded because they're defined by the stencil. So there's actually banded matrices .jl, which what it will do is it just stores this, n by m array where m is the band size. And so it's a cheap way to be able to store just the bands, and then it defines this indexing scheme. And so what we want to do is we want to allow users to be able to call like banded of A and get this special type from banded matrices.jl where these are actual numbers. Since it's actual numbers and actual array, then it can work in different applications where this lazy Julia specific definition can't. Another thing that'd be nice is then to have it be sparse of A, where what you get out is the sparse matrix version of this, so that way you can use modern tools like PETC and Paradiso. It's just now a normal sparse matrix with normal numbers. It'll work with those tools. And then full of A would just give you back the dense matrix. And that could be nice for printing out what the operator looks like. We do have some of these operations, but they don't work in all the cases. And the reason why is because when they get to the boundaries, they don't actually know how to handle multiplication on the boundaries. And so one of them, like full, let me just pull up the issue there. I thought I had a fix before, but then it was wonky. Yeah, so you see that the edges here have a lot of weird stuff in it, while the middles here have the correct stencil. What's going on there is it's trying to use things like a times 1 0 0 0 0 0 to build what the value on the ends should be, what this first row is. That's how you can define a matrix multiplication. But the way that we're handling the boundary conditions isn't working well with it. So this is just using a fallback to linear maps.jl, because this matrix so these operators are actually a linear map from that library. And so the way fallbacks work in Julia is that you get some equations for free. And so this full of A, which defines the full matrix from this multiplication, that's actually for free from linearmaps.jl, but doesn't actually work well for our library. So what we want to do is actually just define a version that works well here, where we actually just put in what the values are, because we know what they should be from the stencil. Not only would that be cheaper than doing all these multiplications, but it will be more correct. And one way to do that is if we define the banded version one, where we have the stencil and then we find out what to do on the ends for the boundary conditions. I think that maybe banded should always return just the stencil. This is something that should be discussed. At least the first implementation should do that. What sparse can do is it can call sparse on the banded matrix, and it can call full can just call full on the banded matrix. And that's an easy way to implement them all correctly, because the banded matrix one is then the most interesting. That's the most useful. The others are mostly fallbacks. So that's the other issue going on there. So okay, that's a not so quick overview of all the things that are going on in DiffEqOperators.jl, why they're interesting, what problems they'll solve, and where we're at. If we can fix up these things with the boundary conditions, following the operators, and fix up some of these tests, then we'll have something that will solve not only the heat equation, the advection equation, KdV, which are our test equations, but then we can use it to solve the Fokker-Planck equation and the Hamilton-Jacobi-Bellman equation, which are famous applications that people actually want to start using this for. And so some of the users, and someone who's actually another mentor on one of these projects, really wants to solve this Hamilton-Jacobi-Bellman equation, and that's how we can get there. So I hope that this video is informative to anyone who wants to start picking this up as just a collaborator, or if you want to do this for a Google Summer of Code project. It's been very informal, and this is my first time using this platform, but hopefully this worked well. As always, if you couldn't tell from the video, you can come to the Skater channel at any time and just ask me questions upon questions upon questions, and I'll be happy to help you out. So yeah, especially if you're looking to contribute, please, please, please feel free to ask questions. I'm always there to help contributors. So I hope that that was informative and that gets us well on our way to doing this project. Thank you.